Hello and welcome to the Thermo Fisher Scientific webinar presentation about the rheological characterization of polymers for 3D printing applications. During this 30-minute presentation, I will talk about the benefits of performing rheological measurements with polymers used for a specific 3D printing technique called fused deposition modeling, or short FDM. So let's have a closer look at the content. I will cover the topics that are shown here, and I will start with some details about polymer-based 3D printing, and I will show the two main techniques used for that. Then I will move on and talk a little bit about polymers in general and their specific flow and deformation behavior. We will have a closer look at the shear conditions in the FDM process, and after that I will provide some theoretical background on how polymer fluids are usually tested for their rheological behavior. With that knowledge, we can move on and discuss the determination of polymer melt viscosity in the shear rate range relevant for different processing techniques. Then we will move on to dynamic mechanical thermal analysis, or in other words, the testing of solid samples in a rotational rheometer. The last part of the presentation will be a short introduction to hyphenated or combined analytical methods. Here I will introduce the combination of rheology with either FTIR or Raman spectroscopy, and I will also show some of the applications where such setups can be useful. I will finish with a short summary of the presentation. So let's start with some details about 3D printing and its relevance for industrial applications. 3D printing is a manufacturing process that enables the relatively quick production of complex structures. 3D printers are nowadays available also for the home market, but when used for industrial application, it is also referred to as additive manufacturing. And there are many industries in which additive manufacturing techniques are already being used, for instance for rapid prototyping or for the production of individual custom-made products. Some of these industries are shown here, and they include automotive, aerospace, pharmaceuticals, and there are even food products that are printed with 3D techniques nowadays. And beside those shown here, there are many other industries that are using 3D printing techniques already quite frequently. When it comes to polymer-based additive manufacturing techniques, we're mainly talking about fused deposition modeling, or short FDM, and stereolithography, or short SLA. FDM is basically an extrusion process where a polymer strand is molten and then forced through a narrow nozzle in order to create a printed part on the lower stage of the printing device. Here, either the upper part or the lower stage is moving, and the printed part is created layer by layer. Stereolithography, on the other side, is using a photochemical reaction to solidify a resin material and create a solid fragment. Also here we have a static and a moving part of the printing device in order to create a product layer by layer. In this presentation, we will focus on rheological measurements describing the rheological properties of a molten polymer as it occurs in the FDM process, and like it is illustrated on the left side of this slide. Before we go into more details of the FDM process, let's first have a quick look at polymers in general and find out why the rheological characterization of polymeric materials is so beneficial for many processing techniques, including 3D printing. Polymers are large molecules that consist of repeating small subunits. These subunits are called monomers, and by adding them via different types of chemical reactions, long, chain-like macromolecules are built. We find polymers everywhere in our daily life, and as a matter of fact, all living organisms contain various types of natural polymers, such as proteins, starch, cellulose, and many others. Many processed food and personal care products contain polymers, thickeners, and stabilizers. And there are, of course, all the products that are made of plastics. When polymers are in a molten state or dissolved in a liquid, they form random coil-like shapes and build very strong intermolecular interactions through entanglements. This three-dimensional network gives many polymer-based liquids and semisolids a quite complex flow and deformation behavior. And the characterization and investigation of this complex behavior can be carried out by means of rheological measurements. Rheology is the study of flow and deformation of matter, and that includes, of course, also all polymer-based materials. Polymer melts are so-called viscoelastic fluids that show both viscous as well as elastic properties. And the highly elastic properties that are present in many polymer melts can lead to different types of flow anomalies. Some of them are shown here at the bottom of this slide. They include the increase in diameter of a polymer strand when exiting a narrow die, for example, at the end of an extrusion line. When the elasticity of a material is even higher, or the processing step is performed at a too high speed, the formation of an uneven surface, also called shark skin, can occur. The effect on the very left is sometimes also referred to as the Weissenberg effect, and it describes the climbing of a viscoelastic fluid up the rotating rod of a mixer or a stirring paddle. In most cases, these are all undesired effects during the processing of a polymeric fluid, and they can all be assigned to the elastic properties of the processed material. Now, when we are looking at the processing of polymers, we basically have to consider the material in two different states. In order to be deformable and flexible, a polymer needs to be in its molten state, which means we need to increase the processing temperature above the glass transition temperature or the melting point. We differentiate between amorphous and semicrystalline thermoplastic polymers. Amorphous polymers do not contain any crystalline domains and therefore only exhibit a glass transition temperature that describes the transition between a deformable solid and a viscoelastic fluid. A semicrystalline polymer, on the other hand, exhibits both a glass transition, where the material transfers into a rubber elastic state first, and then, at even higher temperatures, an additional melting temperature, where all the crystalline domains will disappear and the material converts into a molten fluid. The rheological properties of polymer melts are important for many processing applications, and that also includes polymer-based 3D printing application. Once the polymer melt is blended with other components or simply transferred into the desired shape, it's cooled down again below the melting point or glass transition temperature. Thermoplastic materials are not chemically cross-linked, and the process of liquefying by heating is reversible. However, if the polymer is chemically cross-linked, we distinguish between thermosets and elastomers. Elastomers are rubber-like materials that have, compared to the stiffer thermosets, a significantly lower cross-linking density. Elastomers and thermosets cannot be converted into a free-flowing melt due to the permanent chemical links between them. Now, traditionally, the polymers used for FDM, especially for the home printer market, were often limited to polylactic acid, short PLA, a semicrystalline thermoplastic polyester, and acrylonitrile butadiene styrene, ABS, an amorphous thermoplastic polymer. But for many industrial applications, other materials are needed or desired, and so with further development of 3D printers, many other polymers became available for additive manufacturing. Some are shown here, and they include even high-performance polymers, such as polyether ketone with its extremely high melting temperature. The access to this polymer class makes additive manufacturing even more attractive for many industrial applications. On this slide, you see a schematic drawing of the FDM printing process on the left side with the essential components of the printing device. The polymer is fed into the printer in form of a solid strand, usually coming from a larger drum, and the two counter-rotating rollers are pushing the material into the liquefier, where it's molten and then flows under the pressure of newly fed sample from above into a narrow diameter nozzle. Once it exits the nozzle on the opposite side, it links to either the base plate or the already printed part of the final product. By either moving the upper part of the printing device or the lower base plate, the final product can be created layer by layer. Once the polymer exits the nozzle, the temperature is usually decreased below the solidification point in order to prevent further flowing and to keep the desired shape. From a rheological point of view, especially the transfer of the polymer melt through the narrow nozzle is of interest, and it's illustrated in more detail on the right side of the slide. The flow can be described as a type of capillary flow and is presented here with an idealized laminar flow profile. In reality, we can assume that for a relatively short nozzle, the flow field is not perfectly laminar and shows disturbances, especially at the nozzle entrance. But for a first estimation of the shear rate inside the nozzle, we can use the equation shown on the top of the drawing. This is representing the capillary flow of a non-Newtonian or viscoelastic sample. In this equation, Q represents the flow rate and N the degree of non-Newtonian or shear thinning behavior. Now, for a polymer that is processed in such a way, it is important that its viscosity is not too high, but not too low at the same time either. If the viscosity is too high, it will be difficult for the printing device to create enough pressure to push the material into the nozzle and create a continuous stream at the exit of the nozzle. If the viscosity is too low, on the other hand, the material will flow way too fast through the nozzle and no precise dosing is possible anymore. The correct viscosity of the sample at a given shear condition is usually adjusted by nozzle temperature. Rheological measurements can be used to measure the shear rate depending viscosity of a polymer at different shear rates. Besides measuring viscosity of a polymer sample under different conditions, rheological measurements can be used to investigate and identify many other properties that are important for different processing techniques. An overview of what can be measured with a rotational rheometer is shown on this slide for both solid as well as molten polymers. The information provided by such measurements include the crystallinity or amorphous structure of the tested material, the identification of characteristic transition temperatures. Rheological data can be used to gain information about molecular weight and its distribution. We can identify optimal processing parameters and predict how the final product will behave during application and usage. For reactive systems, we can obtain information about curing, hardening, and cross-linking behavior. And lastly, we can see under what thermal conditions a sample will start to show degradation or decomposition. So we can see that with rheological methods, we have an extremely versatile analytical technique to find optimal processing conditions and to understand the behavior of new formulations or recycled materials. On this slide, we see an overview of the different types of flows that are applied during the various types of rheological testing. We can distinguish between rotational shear flow, oscillatory shear flow, and extensional flow. Experiments with the first type of flow are usually used for determining the shear rate depending viscosity of a material. Furthermore, yielding and thixotropic behavior can be identified, but that is something usually not present when dealing with polymer melts. Commonly used for rheological testing of polymer melts are methods where the sample is exposed to an oscillatory shear flow. Those kind of experiments reveal the viscoelastic properties of a material and can also be used to investigate the stability and to identify characteristic phase transitions. Testing the extensional properties of a polymer is something that is not performed so frequently and is also limited to testing polymer films when using a rotational rheometer. However, the extensional properties are important for many technical applications, and one example from the field of polymers is, for example, film blowing. But in this presentation, we will focus mainly on the conventional oscillatory testing method. The illustration shown here is actually one of the most important in polymer rheology because it explains why polymer melts have a high viscosity and how that viscosity is linked to their average molecular weight. The zero shear viscosity, plotted on the vertical axis, is the constant viscosity of a polymer melt at low shear rates. For polymer melts, the zero shear viscosity strongly depends on the average molecular weight. Below a critical molecular weight, the zero shear viscosity is directly proportional to the average molecular weight. Up to a critical molecular weight, the individual polymer chains are simply not long enough to form intermolecular interactions in the form of entanglements, and the viscosity is only increasing at a moderate and linear rate. However, if the molecular weight exceeds the critical value, the individual chains form a temporary three-dimensional network by entanglements, and the increase of the zero shear viscosity shows a much steeper slope. From there on, the zero shear viscosity is actually increasing for most thermoplastic materials exponentially, with an exponent of around 3.4. The critical molecular weight depends on the molecular structure and the flexibility of the polymer chain and varies for different types. So when we look at the shear rate depending viscosity of a single polymer melt, we usually observe a shear thinning behavior. At low shear rates, they still show a Newtonian plateau. This constant viscosity is often referred to as zero shear viscosity. Once a critical shear rate is reached, the melt viscosity will start to decrease. The average number of entanglements or temporary cross-linking points that are formed between the individual polymer coils is decreasing with increasing shear rate. This plot shows the master curve of a polystyrene melt. The viscosity curve can be divided into three different segments. At low shear rates, we see the constant zero shear viscosity that is linked to the molecular structure of the polymer. At medium shear rates, the viscosity starts to decrease and we observe a transition with a decreasing slope for viscosity as a function of shear rate. The width of this transition depends on the width of the distribution of the molecular weight. The broader the distribution, the wider is also this transition range. At higher shear rates, the sample exhibits a constant decrease in viscosity with increasing shear rate. This is the range that is important for many technical application and processing steps. We see here the typical shear rate ranges for classical polymer processing techniques. And FDM can usually be found in the range between 100 and 1000 reciprocal seconds. Those are the shear rates a polymer melt is exposed to when flowing through the narrow nozzle of a 3D printing device. This slide illustrates different measurement techniques for viscosities in the different shear rate ranges. In order to create a complete viscosity curve that covers all three ranges we have discussed on the previous slide, different measuring techniques are available for the different shear rate ranges. Standard shearing tests with rotational rheometers do usually only give access to the zero shear viscosity range. For viscosity data at higher shear rates, traditionally measurement techniques that utilize capillary flow are performed. These techniques include measurements with instruments like a classical melt flow indexer, but also channel flow tests with specific dies in an extruder setup. However, for most thermoplastic polymers, the widest shear rate range can usually be covered when performing multiple oscillatory frequency sweep tests at different temperatures and utilizing the time-temperature superposition principle, as well as the application of the so-called Cox-Mertz rule. This is also how the plot that is shown on this slide was obtained. We'll see more details about this technique later in this presentation. So on this slide, the comparison of the viscosity curves for three different low-density polyethylene samples, all tested at 190 degrees centigrade, are presented. We are comparing a high molecular weight material, a low molecular weight material, and the blue sample is a 50-50 blend of the high molecular and the low molecular weight sample. We can clearly see the effect of average molecular weight on the viscosity. Especially at low shear rates in the range of the zero shear viscosity, the differences become very obvious. At higher shear rates, the influence of the molecular weight is decreasing and the curves are moving closer together. As mentioned in one of the previous slides, a complete viscosity curve that covers all three characteristic ranges can usually only be obtained by performing rheological tests in oscillation mode. And on this slide, the reason for that is presented. It shows the comparison of viscosity data obtained from rotational and from oscillatory tests. With oscillatory techniques, viscosity data can be measured over a wide range. When using tests in rotation modes, we observe edge fracture effects when exceeding a certain critical shear rate. Here, the sample is not staying inside the measuring geometry of the rheometer anymore, but moving out of it, creating an underfilling and a non-characteristic drop in viscosity. The phenomenon of edge fracture in rotational tests is due to the high elasticity of the sample and typical for most thermoplastic polymers. So when it comes to testing polymer melts with a rotational rheometer, oscillatory measurements are preferred over rotational tests, and this slide provides some brief theoretical background for oscillatory rheology. So either a sinusoidal oscillatory deformation or a sinusoidal oscillatory stress signal is applied by the rheometer. This is also referred to as measurements in CD, controlled deformation, or measurements in CS, controlled stress mode. The response of the tested material is then again either a stress for measurements in CD mode or a deformation for measurements in CS. The important rheological parameters obtained when performing oscillatory tests are presented here at the bottom of this slide. Measurements in oscillation mode allow for quantifying both the elastic as well as the viscous properties of a material. The elastic properties are represented by the parameter G', the storage modulus, and the viscous properties are represented by G', the loss modulus. Whichever is bigger is dominating the overall behavior of the material. Beside the moduli data, oscillatory measurements also provide a value for the phase shift between the input and the response signal, or in other words, the shift between the two sine waves for stress and deformation. A phase angle close to 0 degree describes an almost completely elastic material, like for instance a solid polymer sample. And a phase angle close to 90 degree describes an almost entirely viscous material. Everything higher than 0 and smaller than 90 degree describes a viscoelastic material. The tangents of the phase angle is the ratio between G' and G' and is sometimes also referred to as the damping factor. There are various types of oscillatory measurements that can be performed with a rotational rheometer. An overview of the standard test types is presented on this slide. The amplitude sweep on the left is very often used as a pretest for the other experiments to determine the so-called linear viscoelastic range. During this test, which is performed at a constant frequency, the sinusoidal deformation or stress applied by the rheometer is gradually increased. In the linear viscoelastic range, a material's microstructure remains unchanged, and as a result, the rheological properties, such as storage and loss modulus, are constant and independent of the applied stress or deformation. Once a critical deformation or stress value is reached, the microstructure of the material begins to change, and the rheological parameters also start to change. One of the most important and most frequently used tests when investigating the rheological behavior of polymer melts is the frequency sweep test. The information gained from this test mode is manifold. For instance, shear rate dependent viscosity data can be obtained by utilization of the Cox-Mertz rule. This information allows for quantifying the flow resistance of a material during high shear processing applications, such as injection molding or 3D printing. Temperature sweep tests reveal the behavior of a material at different temperatures. Those tests can be used, for instance, to determine characteristic transitions, such as melting and crystallization. Time sweeps are usually used to investigate thermostability or to follow curing and cross-linking reactions. So coming back to the frequency sweep test, on this slide you see the results of a single frequency sweep test with a polystyrene melt at 190 degrees centigrade. The covered frequency range is limited, and the terminal region at low frequencies as well as the rubbery plateau region at high frequencies do not fall in the covered measuring range. The low and high frequency regions are restricted either by time concerns, and this is simply the duration of a single oscillation, or by the rheometer specifications, and this is the maximum frequency that can be applied by a rheometer. In order to extend the data range beyond the low and high end frequencies, the time-temperature superposition or short TTS principle can be applied. TTS uses the fact that temperature and frequency or time have similar effects on the viscoelastic behavior of polymer melts. As a result, one can perform several frequency sweeps over a smaller range at different temperatures. After selecting one set of data at one temperature as a reference, the other results can be shifted towards the reference curve in order to generate a master curve. By using the TTS principle, it is possible to obtain rheological data over a much wider frequency range compared to a single frequency sweep experiment. The resulting master curve now contains viscoelastic data over almost 8 orders of magnitude in frequency. The master curve can be divided again in 3 regions. At low frequencies, the sample is in the terminal region and the polymer melt behaves predominantly viscous. In the terminal region, materials behavior is mainly governed by long molecule chain relaxation processes. Also, in the terminal region, G' and G" typically have slopes of 2 and 1 in a double logarithmic plots, like it's shown here. At medium frequencies, a transition occurs with a crossover between G' and G". The viscoelastic behavior in this range is strongly driven by the molecular weight distribution of the polymer. At the highest frequencies, the sample behaves predominantly elastic, with G' larger than G". Here, the polymer's behavior is dominated by fast relaxation motion of the shortest polymer chains. And beside the moduli, we also now obtain viscosity data over a wide measuring range, including the relevant ranges for most technical and processing applications. So far in this presentation, we were talking only about the rheological testing of polymer melts. But a rotational rheometer can also be utilized to perform dynamic mechanical thermal analysis, or short DMTA, on solid polymer specimen. During DMTA testing, a material is exposed to an oscillatory mechanical excitation while the temperature is continuously changed. The obtained data is used to identify characteristic phase transition temperatures, such as the glass transition or the occurrence of melting and/or crystallization. In addition, DMTA can be used to determine final product performance and to interrogate relevant application-based properties, such as stiffness, brittleness, damping, or impact resistance. On this slide, you see the so-called solids clamping tool that consists of an upper and a lower clamp, each of them equipped with 2 moving jars. And these jaws here were modified by means of a triangular vertical groove along the center axis. These grooves assure a maximum grip for a specimen with a round profile, such as a filament used for 3D printing. The picture on the right shows a rheometer setup with the solid clamping tool and a PLA filament attached to it. This is a commercially available PLA filament used for 3D printing. Now, with such a setup, data like the one shown on this slide can be obtained. These are the results of a DMTA test with a semicrystalline polyether ether ketone sample, tested from below its glass transition to just below its melting temperature. From this experimental data, the glass transition can be identified using different metrics. The most common matrix uses the maximum in the loss modulus G". So with that technique, we can identify the glass transition temperature for this material at around 165 degrees centigrade. All semicrystalline polymers transition from a glassy region at low temperatures to a rubbery plateau and eventually into the melt state at higher temperatures. The height of the step from the glassy region to the rubbery plateau depends on the degree of crystallinity of the polymer. As the degree of crystalline domains inside the polymer increases, the step height between the two regions will decrease. For processing a high-performance polymer melt, such as PEEK, it needs to be heated up to temperatures above 350 degrees centigrade to obtain a free-flowing polymer melt. Now this slide shows the results of a similar experiment, but this time carried out with the PLA filament used for 3D printing applications. The test was performed over a temperature range from 30 to 160 degrees centigrade. At low temperature, the material was again in its glassy state and showed high values for the storage modulus G' and the loss modulus G'. In this state, G' reached values of around 10 to the 9 Pascal and was about 2 orders of magnitude larger than G'. The resulting value for tang delta of around 0.01 indicated that PLA is a rather brittle material at ambient conditions. Up to a temperature of around 60 degrees centigrade, G' remained nearly constant, while G' was increasing continuously. At 62 degrees centigrade, G' reached a maximum, which can be considered again as a measure for the glass transition temperature. With further increasing temperature, both moduli dropped almost 3 orders of magnitude into a low rubber elastic plateau. And now the surprising part happens. At temperatures between 90 and 100 degrees centigrade, the values for both moduli started to increase again rapidly before reaching another plateau region. At temperatures above 140 degrees centigrade, the sample started to melt and both values were decreasing again. The increase in moduli between 90 and 100 degrees centigrade can be assigned to a phenomenon called cold crystallization that occurred above the glass transition and below the melting point. Cold crystallization only occurs when the original specimen was processed in a way that included a rapid cool down from melt into the solid state. In those cases, the PLA chains do not have enough time to align and form crystalline domains before reaching the glass transition temperature. Below the glass transition temperature, the mobility of the molecules is reduced so much that no further crystallization will occur anymore, and the PLA shows a dominantly amorphous structure. Now here you see the comparison of the previous data with the DMTA test performed with the PLA filament with a different thermal history. Prior to the test, the specimen was heated to 130 degrees centigrade, so above the cold crystallization temperature, and afterwards cooled down below its glass transition temperature, but not rapidly, but rather with a slow cooling rate of 2 Kelvin per minute. It can be seen that in this case no cold crystallization occurs anymore, and the material showed the thermo-rheological behavior of a typical semicrystalline thermoplastic material with a broad, rubbery elastic plateau at temperatures above the glass transition and below the melting point. Now what we can learn from this example is that rheological measurements can be used to obtain information about the degree of crystallinity and the thermo-rheological history of a material. Now the degree of crystallinity, as well as how rapidly a semicrystalline polymer is recrystallizing once it's cooled down from the melt state to below the melting point or even the glass transition temperature, is an important information for many technical processes, including FDM. Once the molten polymer is leaving the printing nozzle of a 3D printing device, the temperature is dropping and recrystallization can occur. The kinetics of the recrystallization process can have an effect on how well the newly printed material is connecting to the upper layer of the already printed part. In order to study the crystallization kinetics of semicrystalline polymers in more detail, a combination of rheology with another analytical technique has proven to be useful. For a deeper understanding of structure-property relationships in general, usually more than one analytical technique is required. When combining rheometry with other analytical techniques, additional information can be obtained. On this slide, two rheometer setups are presented that are coupled either with an FTIR spectrometer, shown on the left, or a Raman spectrometer, shown on the right. Both setups allow for simultaneous rheological and spectroscopic analysis of a material. The FTIR coupling can be used, for instance, to study the kinetics of curing and cross-linking reactions, for example, those that occur in stereolithographic printing processes. With the Raman coupling, changes in the crystallinity of a polymer melt during a rheological experiment can be monitored. Some technical details of the Rheo-Raman coupling are shown here. The laser light coming from the Raman spectrometer is directed through a system of various optical components into the bottom stage of the rheometer. The lower part of the rheometer contains further optical components, and the light is introduced to the sample through a glass plate from the bottom. The backscattered part of the light is now going back to a detector inside the Raman spectrometer. This setup allows for simultaneous rheological and spectroscopic measurements with exactly the same sample up to temperatures of 300 degrees centigrade and is therefore ideal for the investigation of polymer crystallization kinetics. Some example data for the isothermal crystallization of polypropylene is shown here on this slide. The formation of crystalline domains is linked to Raman signals at specific wavelengths. At the same time, the overall mechanical behavior of the sample during the phase transition is investigated with rheological measurements. With this technique, different ranges of the solidification process of the polymer during cool down can be distinguished. For more details on this setup and other example data, please also check our website for further information, including various product and application reports. And this brings me to the last part of this presentation, where I would like to make a quick summary of what I presented on the previous slides. So the takeaway messages are: rheological behavior of polymer melts plays an important role for many processing techniques, and that includes, of course, also 3D printing. Polymer melts are so-called viscoelastic materials, and they show a rather complex flow and deformation behavior. Rheological measurements, especially those in oscillation mode, can be used to determine the shear rate depending viscosity of polymer melts in all the shear rate ranges that are relevant for most technical applications. And besides the determination of viscosity, rotational rheometers can also be used to perform dynamic mechanical thermal analysis with solid specimens. And those obtained results are usually used to investigate application-related properties of the printed part, and that includes stiffness, brittleness, and damping properties. They can be used to determine phase transitions, like the glass transition temperature, and also have a look at the degree of crystallinity and the thermorheological history of a material. And finally, combining rheology with other analytical techniques allows for a more comprehensive study of structure-property relationships of polymer melts. And that also includes a more detailed investigation of crystallization processes. And with this, the presentation is finished. Thank you very much for watching. And please also have a look at our website for further information and additional content such as webinars, application reports, and videos. And with that, I say goodbye and until next time.